Let's talk about using parametrics for simple motions. We're not going to be doing calculus yet, more about math modeling. Let's say an airplane is currently at an x position of 10, let's say like 10 kilometers east of an airport and 30 kilometers north of the airport. And let's say it's headed to exactly northeast at 5 kilometers per minute in x, 5 kilometers per minute in y. To be headed exactly northeast, these two numbers have to be the same. If its speed in the x direction was different than its speed in the y direction, it wouldn't be heading exactly along a 45-degree line, right? So write a parametric description of its position. Pause the video while you try writing that out and maybe sketch a graph too. All right, welcome back. So sketching a graph is not a bad idea. So we'll say here's 10, here's 30. The plane is currently at that position. It's heading northeast, so north would be that direction, east would be that direction. So the plane is heading this direction. So we'll do a compass rose here, like that. So that's kind of its current position and its velocity vector, maybe. We'll talk more about that later. What can we say for its x position as a function of time and its y position as a function of time? I should note that this axis is the east-west location in kilometers. This axis is the north-south location, again in kilometers. There's two ways of writing it, one of which works better with Desmos, the other one maybe is more intuitive or a little cleaner. We could write my x position at time t is something, and my y position at time t is something. We didn't say what to use for t. Minutes, hours, seconds? What do you think works best here? Well, we've got minutes in the problem, so maybe minutes is good there. So we could say, we didn't say this here, but we could decide that t equals 0 minutes is now. That's not on the y-axis here, that's just a side note. So t equals 0 is now. So I could say my x value starts at 10 and increases at 5 kilometers per minute for every minute that we go forward from now. And then what would you say for y of t? It starts at 30 and increases at 5 kilometers per minute for every minute that I go forward from now. You could also plug in negative t values here, and that would predict where the airplane was a minute ago or 2 minutes ago, kind of before now. So that's not a bad idea. So that is a perfectly good mathematical description of the plane's location, but Desmos won't be happy with it. So let's divide this up. So what you'd say in Desmos is f of t equals 10 plus 5t, g of t equals 30 plus 5t, and then put a point at f of t comma g of t. And you'd have to define your time range. You could go 0 less than or equal to t less than or equal to. How many minutes in the future do you think this description is going to be valid? Probably 1 at least, maybe 10. I'm not sure how often airplanes change. Depends on what kind of plane it is, I guess. So I'm just going to put 10 minutes there. You don't have to tell Desmos the units, but just for our own context knowledge. So the problem with this in Desmos is that x and y are special letters to Desmos for obvious reasons. And so we have to not use x and y when we define things and let it figure out x and y from doing an ordered pair here. So now here's another question. Let's say you have a second airplane that's at 2030 right now. And it's at the same altitude, the same height above the ground. And it's heading exactly north at 4 kilometers a minute. Go ahead and write a parametric description of its location. So pause the video while you do that and then come back. Okay, so I would say like f2 of t for the second plane equals its current x position plus what's its east-west velocity. F and x are about east-west. What's its east-west velocity? 0, because it's heading exactly north. So it would be 0 times t. g2 of t equals 30 plus 4 kilometers per minute times t. And then if we graph those, we've got our original plane doing this here at 10:30. And our second plane is at 20:30. Do this in another color. And it's heading exactly north. So when you graph those parametric curves, they're going to cross. Are the planes going to hit each other? Or if they don't hit each other, how close do they come? Are they like 3 meters apart? That would not be good. 3 kilometers apart, we could probably live with. So we're saying, do the planes hit each other? Well, let's go try it all in Desmos. Alright, so I've got my location of airplane 1 in x and y, and then plotting it on the time range 0 to 5. And then I've got my x and y location of airplane 2, plotting that again on the range 0 to 5, and we see that their paths intersect here. But let's try to figure out whether the airplanes themselves will crash. We can do the same trick we did before and only plot this for t values less than some cutoff, like capital T. And we'll do the same thing down here. And we can even put a point at f1 of t, capital T, g1 of capital T. That'll put a point right where our first airplane is. And f2 of capital T, g2 of capital T. And now as I, we'll start there. So now as I increase time, we can see that those two planes, oh, they're getting pretty close to each other, but they never quite occupy the same point at the same point in time. So they're not actually going to collide. I would not be comfortable if I was on that flight, I think. I mean, I guess they're still a kilometer apart here, but there's probably rules for how close airplanes can get. And 1 kilometer feels like it's a little too close to me. So the big lesson here about parametric curves is just because two parametric curves cross in the plane doesn't mean that the functions themselves are at that point at the same point in time. So sometimes we want to ask, if I have two curves crossing each other, at what time point did this curve get to that intersection point, and at what time point did this other curve get to this intersection point, like that. And you can do that in Desmos by setting up a simulation like this and playing around with it. You can also set up equations like, if you know where they cross at 20, 40, you could set f of t, f1 of t and g1 of t to 20, 40, and say 10 plus 5t equals 20, 30 plus 5t equals 40, solve for t, and you would find what time point the first airplane was at that intersection point, and then do the same thing here.